Now we're taking a new look at elastic collisions and wondering, is there something else that is conserved? We've talked about momentum, yes, but is anything else conserved? So elastic, or what you might call bounce apart collisions, occur with varying degrees of bounce. So if you throw a basketball against a wooden wall, it's going to have a different amount of bounce than if you threw a golf ball at, say, concrete or bricks. So we have four situations here. A, hitting a softball with a wooden bat. B, hitting a baseball with an aluminum bat. C, a golf ball with a driver. And D, a steel ball with a steel pipe. And so we're going to be asking ourselves four questions about these. So which collision deforms the ball the most? So when two objects collide, there tends to be a change in shape. And especially with something like a softball or a baseball, it doesn't stay as a perfect sphere when you hit it with a bat. There will be some amount of essentially squishing the ball, and then the ball will recover its shape once it has changed directions. So we have to look at both these things, the ball and whatever you're hitting it with. So if you look at the first two, a softball and a baseball, there's not a whole lot of difference between these two in terms of how much give the ball has, how much it will deform. Baseballs are really tightly wrapped with this string or twine on the inside of the leather cover, and a softball tends to be more of a solid composite. And they're very similar. You could argue for both, which one deforms the most. But I think that a softball would probably deform a little bit more than a baseball. Just because softballs tend to be more affected by things like temperature. On a really hot day, a softball tends to have a lot of give. On a really cold day, it feels like a rock. Then we also have to consider what type of a bat are we hitting it with. Now, a wooden bat, usually made out of ash or maple, very hard wood, very little give. And so we have an object with quite a bit of give and an object with absolutely no give. And so in this collision, if anything's going to give, it's going to be the ball. Then hitting a baseball with an aluminum bat. Now, even if we said that a baseball and a softball have the same amount of give, we have a different bat. And an aluminum bat has a lot more pop to it because the bat will slightly change its shape when it contacts the ball, and then it springs back to its original shape. And so in these two scenarios, I'd say it has more to do with the bat than it does the ball. So this bat has a lot of give, which means the ball will be deformed less than this situation with the softball. So I'm going to go with A here. The softball against a wooden bat is going to lead to the most deforming of the ball. So which collision deforms the ball the least? So if you look down the list, you've got a golf ball, which is pretty hard as far as balls go, with a driver. And then you've got a steel ball with a steel pipe. Which one of these two is going to deform the most? Which one's the least? I don't know exactly how much give a golf ball has. If nothing else, it's got a plastic cover that's going to have a little bit of give. I'm going to say that it probably will deform a little bit more than a steel ball. Steel is very strong, very hard, probably not going to deform very much. And then consider what you're hitting them with. So a driver, it's going to have some give because of the shaft part of the driver. But a steel pipe is going to have no give whatsoever. So neither the steel ball nor the steel pipe are going to have almost any give at all. And so I'm going to say that this one probably deforms the shape of the ball the least out of this list. A different look at it, which collision is the least elastic? So an elastic collision is one where the two objects collide and then they bounce apart. So the least elastic is the one where they collide and they would exit the collision with the least amount of maybe velocity. So they hit and they're slower after the fact. So which one's the least elastic? And this would be the one with the most give, or the one with the ball that deforms the most, because a lot of energy is going to be taken to change the shape of the ball. Less of it remains for the ball's velocity as it leaves. And which collision is the most elastic, least likely to lose energy due to a change in shape? And that would be the one where the ball deforms the least. And so if you look, the one where the ball deforms the most is also the least elastic. And the one where the ball deforms the least is the same as the most elastic. We have some answers at the right. Use them only once. If we throw a softball at a concrete wall at 20 meters per second, it will bounce off the wall at perhaps, and let's draw a picture first. So here's what's happening. So here's the wall. Here's our ball coming in at 20 meters per second. It's going to hit the wall and then it's going to fly off in the other direction. Now, what are the chances that it's going to return at 20 meters per second? It's unlikely, but let's talk. If we throw a softball at this concrete wall at 20 meters per second, it might bounce off at maybe 12 meters per second. If it's a baseball, which we said there's some debate, but maybe a little bit harder, maybe it's got just a little bit of a higher exit velocity, maybe 15 meters per second. If it's a golf ball, remember that's a more elastic collision. It might bounce off a little faster at 18 meters per second. But there is no ball that will bounce back at 20 meters per second, because there must be some loss of energy when the ball hits the wall. And it goes into a few places. The first thing you'll notice when you hit a ball against the wall, there's noise. Noise is sound waves, that's energy being lost. There's also going to be a very small amount of heat that is lost in this collision. It's not going to be easy to measure it. There's a little bit of heat energy. There's also a little bit of energy that goes into deforming the shape of the ball and then returning its shape to the ball. So you're losing energy in several different places, which is why none of these quite make it up to 20. You can't make it close. There's a new concept. It's the energy of motion, or what's called kinetic energy. So think of an elastic collision in which there's no loss of energy due to deforming objects. This is called a perfectly elastic collision. So there is no loss of energy. If you drop a basketball from a height of 2 meters, it might bounce to a height of 1.1 meters. This is just an estimate. A tennis ball, they're fairly bouncy, bouncier than a basketball, maybe 1.2 meters. A golf ball, maybe 1.6 meters. But if the collision were perfectly elastic, it would bounce to a height of 2 meters, which means there would be no loss of energy due to the collision. Are there actually perfectly elastic collisions in this universe? Perfectly elastic collisions occur in nature only between atoms and subatomic particles. This is the only place with perfectly elastic collisions. If you talk about air molecules, they come very close. And switching gears to chemistry, the kinetic molecular theory says one of its assumptions is that the collisions were perfectly elastic. Collisions between steel balls, billiard balls, silicone rubber balls, they conserve a lot of energy, somewhere maybe up to 95% of the original. This leads us into a new law of conservation. This is the conservation of kinetic energy. Kinetic energy is the energy of motion. Energy of motion. The formula, which we look into more in depth in Unit 7, kinetic energy equals 1/2 times the mass times the velocity squared. So looking at the formula, for something to have kinetic energy, it has to have two things. First off, it has to have mass. Secondly, it has to have velocity. These are the same two things that we need for an object to have momentum. And remember, momentum equals mass times velocity. But the kinetic energy formula, the velocity is squared, which makes some differences. Momentum is a vector. It's a vector because velocity is a vector. It has direction. An object's momentum is in the same direction as its velocity. But kinetic energy is not a vector. And this is because velocity is a vector, but velocity squared is not a vector. You can square velocity, and the number will be squared, and the units will be squared. But how do you square direction? So velocity squared, not a vector. So if you look at the velocity, if the velocity is doubled, the momentum is also doubled. But the kinetic energy, since we have to square it, is quadrupled. If velocity tripled, momentum is tripled. But kinetic energy is 9 times as great. So the law of conservation of kinetic energy works a lot like the conservation of momentum. In words, the total kinetic energy of a closed system is constant. And the reason I have special here is because a closed system doesn't usually exist. This is something where there are no outside factors to be considered. And so it's pretty rare to have a closed system, maybe impossible. But that's why it says special. In easier words, total kinetic energy before equals total kinetic energy after. Here is where the conservation of kinetic energy has a formula, and we use 1/2 mv squared for kinetic energy. But consider two objects, 1/2 mass of object A times the velocity of object A squared, plus 1/2 times the mass of B times the velocity of B squared equals 1/2 mass of A, new velocity of A squared, plus 1/2 mass of B times velocity of B, the new velocity of B squared. And it's going to work in a manner very similar to our other conservation law. So this is very important. The law of conservation of kinetic energy only works in perfectly elastic collisions. This is where there is no loss of energy in the collision. So we use it in the collisions of steel balls, etc., because those collisions tend to come close to being elastic, but most things don't. Question: are these quantities conserved in these collisions? Is momentum conserved in an inelastic collision? Yes. This is a collision where two objects collide and they stick. It's a hit and stick collision. What about a partially elastic collision? Is momentum conserved? Yes. In a perfectly elastic collision, yes, momentum is still conserved. Does kinetic energy work in a perfectly elastic collision? It does, that's what this says, but it only works in a perfectly elastic collision, which means it doesn't work in a partially elastic collision, and it doesn't work in an inelastic collision. It only works when the collision is perfectly elastic. So what happens to the rest of the kinetic energy? Again, this is a topic of a future unit, but we'll ask the question now. What happens to the energy lost in the collision when a basketball hits the floor and doesn't bounce up with the same energy? What happens in the collision between the golf ball and the driver if the kinetic energy of the driver before the collision doesn't equal the sum of the kinetic energies of the ball and driver after? In the case of the basketball, some of the kinetic energy is imparted to or absorbed by the earth. And some of the kinetic energy goes into the form of heat energy. The ball and the floor are both getting warmer. In the case of the driver and the golf ball, the kinetic energy lost becomes heat energy. Both of these objects are heating up. Example 10, find the kinetic energy of each object. Football player, mass 90 kilograms, velocity 7 meters per second north. Find the kinetic energy. KE, kinetic energy, equals 1/2 times the mass times the velocity squared. 1/2 mass is 90 kilograms. Velocity is 7 meters per second. We're going to square the whole quantity. And we come up with 2,205 kilograms times meters squared per second squared. And if you look at all of this, a kilogram times a meter per second squared is a Newton. And then you have meters left over. Newtons times meters, there's a name for this. Joules. What's the kinetic energy of the space shuttle? Again, starting with a formula, 1/2 times mass times velocity squared. Mass is 10 to the 5th kilograms. Velocity is 7,600 meters per second to the east, and that's quantity squared. We come up with 2.89 times 10 to the 12th. Units or joules? How about a mosquito? Kinetic energy, 1/2 times the mass times the velocity squared. Mass is 10 to the -4th kilograms. Velocity, 30 centimeters per second. Square that quantity. Since we're talking about kilograms, seconds, newtons, joules, really we should change this to be in terms of our family of units. So let's go back up here and convert this. So velocity is 30 centimeters per second. And there are 100 centimeters in a meter. We have 0.3 meters per second. It's a lot easier to convert this before you square the quantity than after. And we end up with the kinetic energy of the mosquito being 4.5 times 10 to the -6 joules.